Hello, dear students. We start our lesson. Today is Team 14. The name of our team, Advanced Methods of Material Processing. And the plan of our lecture, write down to your notes our plan. 14.1, General information about electrophysical, chemical, technological processing. Process in mechanical engineering. 14.2, beam and ultrasonic methods of material processing. 14.3 efficiency of new methods of metal processing. And 14.4 technical and economic characteristics of the use of new methods of processing materials. So write down to your notes the theme of our lecture and the plan of our lecture. And we start item 14.1, general information about electrophysical, chemical, technological processing in mechanical engineering. So when processing metals by cutting, obtaining parts of the required dimension is achieved by removing chips from the workpiece surface being processed. Chips are thus one of the most common wastes in metalworking, amounting to about 8 million tons per year. At the same time, at least 2 million tons are waste from the processing of high alloy and other especially valuable steels. When processing on modern metal cutting machines, up to 30–40% of the metal from the total mass of the workpiece often goes into the chips. Therefore, more and more attention is being paid to new methods of metal processing based on waste-free or low-waste technology. The emergence of new processing methods is also due to the explaining use in mechanical engineering and other sectors of the national economy of high-strength, corrosion-resistant, and heat-resistant metals and alloys, the processing of which is difficult by conventional methods. New methods of metal processing include chemical, electrical, plasma, laser, ultrasonic, and heteroplastic metal processing. A decisive role in accelerating technical progress in mechanical engineering belong to new progressive technological processes that can dramatically increase labor productivity, reduce labor intensity, and increase the reliability and durability of products. In the practice of metalworking, electrophysical and electrochemical methods are beginning to occupy one of the leading places. The share of technological operations performed by these methods in the total volume does not yet exceed 1%. However, their use has made it possible to significantly reduce the difficulties of introducing hard alloys, facilitate the transition to the widespread use of difficult-to-process materials, including non-metallic ones, and solve a number of complex technological processes, takes associated with the production of products from materials that have not previously been processed. So, chemical and electrical processing methods. The main difference between electrophysical and electrochemical methods and mechanical processing by cutting or pressure is the direct use of electrical energy or physical and chemical phenomena created with its help as a processing tool. The technological use of electricity for processing materials is characterized by such important features as practical independence of the speed, quality, and productivity of processing from the physical and mechanical properties of the materials being processed, high technological flexibility of processing processes, no need to use special tool materials with high hardness, strength and wear resistance, significant reduction in material consumption, suitability for performing a number of operations that cannot be performed by other processing methods, relative simplicity of the technological process and simplicity of the equipment, the possibility of local processing of large-sized products without the use of special machines, the possibility of complete automation and mechanization of processing processes, improvement of working conditions, etc. Progressive processing methods can be divided into two groups. The first includes methods used to remove material from treated surfaces, transfer it and shape it using electrical energy introduced directly into the treatment area. These are electroerosive, electric shock, electric pulse, electric contact, anodic mechanical processing, and electrochemical methods. It's the second group. Electrochemical methods, electrochemical, mechanical, and other types of processing. The second group includes methods with preliminary conversion of electrical energy outside the working area into other types. These are light beam, electron beam, ultrasonic methods, etc. There are many combined processing methods, including elements of both the first and second groups. First group and second group. Electrophysical and electrochemical methods of processing materials are successfully used at virtually end stages of productions. Using these methods, many operations of pre-processing are carried out. Cutting and peeling of workpieces, cutting of getting systems, removing allowances, etc. Dimensional processing, manufacturing and processing of parts of complex configuration. Finishing and precision processing. Surface hardening, grinding, polishing, as well as a lot of restoration work, repairing dies, removing broken tools, etc. Chemical processing use chemical energy. A certain layer of metal is removed in a chemical active environment, chemical milling. It consists in time and place controlled dissolution of metal from the surface of products by etching in acid and alkaline baths. Surfaces that cannot be treated are protected with chemically resistant coating. The constancy of the etching rate is maintained due to the constant concentration of the solution. Using chemical processing methods, local thinning is obtained on non-right workpieces, stiffening rib, winding grooves, and crevices, waffle surfaces, process surfaces that are difficult to reach with cutting tools. With the electrical method, electrical energy is converted into thermal, chemical, and other types of energy directly in the process of removing a given layer. In accordance with this, electrical processing methods are divided into electrochemical, electroerosive, electrothermal, and electromechanical. So, electrical processing methods. First, electrical processing method, it's electrochemical processing, is based on the laws of anodic dissolution of metal during electrolysis. When a direct electric current passes through the electrolyte, chemical reaction occurs on the surface of the workpiece, which is connected to the electrical circuit and serves as the anode, and compounds are formed that go into solution or are easily removed mechanically. Electrochemical processing is used for polishing, dimensional processing, honing, grinding, cleaning metals from oxides, rusts, etc. Next type of electrical processing methods, it's electrical discharge machining. Electrical discharge machining is based on the laws of erosion, destruction of electrodes made of conductive materials when a pulsed electric current is passed between them. It is used for saving cavities and holes of any shape, cutting, grinding, engraving, sharpening, and straightening tools. Depending on the parameters of the pulses and the type of generators used to produce them, electrical discharge machining is divided into electric spark, electric pulse, and electric contact. Electroerosive methods of metal processing are based on the use of the phenomenon of electrical erosion, in which the local thermal effect of electric current pulses is manifested. An electrical discharge occurs between two electrodes, the tool and the workpiece. The repetition of pulses causes the metal layer to be removed from the part, resulting in the formation of a depression corresponding to the shape of the tool surface. Electric spark machining of metals is used for processing hardened steels and hard alloys, drilling holes of small diameters in millimeters, Production of profile narrow grooves and grooves-shaped interval cavities in dies, molds, cutting tools, blind holes in tapes and their drills after breakage from expensive parts, cutting workpieces, etc. The process is carried out on special machines, like in figure 14.1. You can see scheme of electric spark processing of metals. Special machine equipped with electric current pulse generators. Generator pulset consists of a direct current generator G, resistance K, and capacitor C, and contains capacitor C. During processing, the electrode tool serves as a cathode, and the workpiece tool serves as an anode. The processing is carried out in a dielectric fluid environment. As the capacitor charge between electrodes 2 and 3, the voltage increases and an electric field arises, causing ionization of fluid molecules. At a certain degree of ionization, a breakdown of the dielectric liquid occurs and a flow of electrons rushes through the discharge channel onto the workpiece and at enormous speed. Due to the small cross-section of the channel, the energy density in it reaches enormous values. As peak discharge, the duration of which is 10 to the power minus 6 seconds, causes a large thermal effect with temperature up to 10,000 degrees of Celsius. Under such conditions, melting and partial evaporation of small portions of metal occur in the processing zone, which has the nature of an explosion. The ejected molten metal particles are cooled by the liquid and sink to the bottom of the batch. After the discharge has passed, the voltage on the electrodes drops and the electrical neutrality of the medium is restored. The pulse frequency ranges from 150 to 1000 Hz. A constant interelectrode clearance is automatically maintained by a special regulator. Tool electrodes are made of copper, brass, cast iron, aluminum, and in some cases, tungsten. Mineral oil, kerosene, distilled water, and other dielectric liquids are used as dielectric liquids. Accuracy during electrical discharge machining of holes reaches plus minus 0.01 millimeters. Surface roughness is 6-7 classes. The disadvantages of the electric spark method include the relatively low productivity when processing steel metal removal reaches 0.8-0.9 centimeters to the power 3 per minute. High energy intensity, 36 to 152 megajoule, 1070 kilowatt per 1 kilogram of removed metal, and high consumption of electrodes. The use of electrodes made of graphite and copper tungsten compositions results in a significant reduction in electrode consumption and an increase in productivity. At a certain value of the potential difference on the electrodes, one of which is the processed workpiece, anode, and the other is the tool, cathode. A conductivity channel is formed between the electrodes through which a pulsed spark, electric spark processing, or arc, electric pulse processing, discharge passes. As a result, the temperature on the surface of the workpiece increases to 5 or 10, from 10 to 12 multiplied by 10 to the power 3 degrees of Celsius. At this temperature, an elementary volume of metal instantly melts and evaporates, and a hole is formed on the surface of the workpiece being processed. The removed metal hardens in the form of small granules. The next current pulse breaks through the inter-electrode clearance, where the distance between the electrodes is smallest. With continuous supply of pulsed current to the electrodes, the process of their erosion continues until all the metal located between the electrodes at a distance at which electrical breakdown is possible is removed. 0.01, 0.05 millimeters at a given voltage. To continue the process, it is necessary to bring the electrodes closer to the specified distance. The electrodes are brought closer together automatically using a tracking device of one type or another. Electric spark processing is used for the manufacture of stamps, molds, dies, cutting tools, parts of internal combustion engines, meshes, and to strengthen the surface layer of parts. Electric pulse processing. Electric pulse processing is used as a preliminary treatment for dies, turbine blades, and surfaces of shaped holes in parts made of heat-resistant steels. With electric pulse processing, the metal removal rate is 8-10 times higher than with electric spark processing. The electric pulse methods of metal processing arose as a result of the improvement of the electric spark method. When processing with this method, the part is connected to the negative pole of the powder source, and the tool is connected to the positive pole. The main influence on the threaded surfaces is exerted by positively charged ions. The duration of electric current pulses created by special generators is 10 to the power minus 3 seconds, which is significantly longer than during electric spark machining, the shape of which contributes to directing all the energy only to the distribution of the metal of the workpiece being processed. This made it possible to significantly reduce the temperature in the inter-electrode clearance up to 4,000–5,000 degrees, reduce tool wear, reduce power consumption, and use graphitized materials for electrodes, providing higher operating conditions. The productivity of electric pulse processing can reach 8–10 centimeters to the power 3 per minute or more. The processing accuracy and surface roughness depend on the selected processing mode. In soft modes, processing accuracy reaches 8–9 grades, and surface roughness reaches 5–7 grades. It is advisable to use electric pulse processing when simultaneously removing metal from relatively large areas and blank processing, since in this case the productivity of the process sharply increases. Providing translation or rotation motion to the electrodes during electric spark and electric pulse processing makes it possible to reduce the manufacturing time of parts by 1.5–2 times due to an increase in lateral clearances and easier evacuation of erosion products from the inter-electrode clearance. Recently, high-frequency electric pulse processing has become widespread. It allows you to process parts to class 9 surface roughness with a productivity of from 30 to 50 times, which exceeds the productivity of the finishing modes of the electric spark method. Low pulse energy ensures low roughnesses of the machining surface, and high pulse repetition frequency from 20 to 40 kHz ensures greater productivity. The pulses are generated by special tube generators. The processing is carried out in an environment of kerosene of water, which is forcibly pumped through the clearance between the electrode and the workpiece. Copper is used as the material for the tool. Anodic mechanical processing combines electrochemical and electromechanical processes and occupies an intermediate place between electrochemical and electroerosive methods. The workpiece being processed is connected to the anode and the tool to the cathode. Metal discs, cylinders, tapes, and wire are used as tools. The treatment is carried out in the middle of the electrolyte. The workpiece and tools performs the same movements as in conventional machining methods. The electrolyte is fed into the processing zone through a nozzle. When a direct electric current is passed through the electrolyte solution, the process of anodic dissolution of the metal occurs as an electromechanical processing. When a tool, the cathode, touches the micro roughness of the workpiece surface being processed, the anode, the process of electrical erosion, characteristic of electric spark machining, occurs. Products of electrical erosion and anodic dissolution are removed from the processing zone when the tool and workpiece move. The process of anodic mechanical processing of metals is based on electrochemical and electrical erosion destruction of metal. It is used for cutting hard materials, sharpening carbides, cutters, cutting shaped grooves, grinding flat and cylindrical surfaces, etc. The anodic mechanical treatment scheme is similar to the electrical contact scheme. The process is carried out in an electrolyte environment, aqueous solution of liquid glass or salts. The workpiece being processed serves as the anode and the tool rotating disc serves as the cathode, which is applied to the workpiece under slight pressure. When direct current flows under the influence of an electrolyte, the surface of the workpiece dissolves with the formation of an electrically conductive film of dissolution products. The film is continuously destroyed by a rotating disc. If the tool comes into contact with the workpiece along protrusions exposed from the film, short-term arc discharges occur in these small areas of the processed surface. The disc is made from copper, milled steel, cast iron, etc. The productivity of anodic mechanical treatment depends on the selected mode and ranges from 2 to 6 centimeters to the power 3 divided by minute when cutting end from 2 to 6 millimeters to the power 3 per minute when grinding. The surface roughness when cutting is obtained in the range of from 2 to 4 classes, and when grinding in the range of from 9 to 11 classes. The processing accuracy when cutting reaches 11th grade, and when grinding from 6th to 5th grade. Next type of processing, electrical contact processing of metals, consists in the fact that when the electrode tool is quickly moved, rotated relative to the workpiece being processed, connected to an alternating of or direct current source, short-term arc discharges and are formed at the moments of contacts. As a result, The surface layer of metal is heated, melted, and removed by a rotating tool. The process is carried out in an environment of mineral oil, water, or air at a voltage of from 2 to 20 volt and slight pressure from one electrode to another. The electric contact method is effective when performing raw operation, cutting, stripping castings, descaling, etc. It provides processing accuracy of 11-12 grades and surface roughness of 1-2 grades. A steel disc is used as a tool for peeling and cutting, and a metal brush is used for cleaning. Process performance is raw mode reaches 700 centimeters to the power 3 per minute. The specific energy consumption when processing steel is 6.5 megajoule, 1.4-1.8 kilowatt per 1 kilogram. Next type of processing, electromechanical processing, is mainly associated with the mechanical action of electric current. This is the basis, for example, of electrohydraulic processing, which uses the action of shock waves resulting from pulsed breakdown of a liquid medium. Hydroplastic processing of metals. The production of metal hollow parts with a smooth surface and small tolerances. Hydraulic power cylinders, plug-ins, housings for electric motors, carriage axles, some gears, is increasingly being done in recent years, not by removing chips, but using so-called hydroplastic processing. A hollow cylindrical blank or workpiece, heated to the temperature of plastic deformation, is placed in a massive split matrix made according to the shape of the part being processed, and the water is pumped under pressure. The workpiece or blank is distributed and takes the form of a matrix. To manufacture, for example, a carriage axle, a pressure of 150 megapascal is required. Therefore, the analyzed method does not allow the production of parts of significant size, for example, pipes. But if you make sure that when water gets inside the workpieces and collides with hot metal, it instantly turns into steam, its volume will increase many times over. Due to this, the workpiece will be pressured thickly against the matrix. Only 10-20 megapascal steam pressure is required. The implementation of this idea in our country made it possible to eliminate drilling and other types of machining in the manufacture of hollow parts. Another effect is achieved. The metal of the part becomes denser and finer grained under pressure. Parts made in this way have higher durability. Using a new method, it is possible to produce bimetallic pipes by placing two blanks, one inside the other, in a matrix. Such original installations are also possible, performing various operations from punching holes in foil to production hemispheres from steel metal of considerable thickness. Ultrasonic processing of metals. A type of mechanical processing is based on the destruction of the material being processed by abrasive grains under the impact of an oscillating tool with an ultrasonic frequency. The energy source is electrosonic current generators with a frequency of 1630 kHz. The working tool, the punch, is fixed on the waveguide of the current generator. A workpiece is placed under the punch and a suspension consisting of water and abrasive material enters the processing zone. The processing process consists of a tool oscillating at an ultrasonic frequency and strikes abrasive grains lying on the surface being processed. Which chip of particles of the workpiece material? The processing speed depends on the frequency and amplitude of vibration, the hardness and size of the abrasive particles. Ultrasonic vibration of the tool are created using magnetic restrictive vibration that convert electrical energy into mechanical energy. Ultrasonic processing is used to produce carbide inserts for dies and punches, cutting out shaped cavities and holes in parts, engraving, stitching holes with curved axes, threading, cutting workpieces into parts and other works. The dimensional accuracy of parts and the roughness of their surfaces processed by ultrasonic methods depend on the grain size of the abrasive materials and correspond to those obtained during grinding. Plasma laser processing. Beam or laser processing methods are based on the use of a focused beam, electronic coherent ion with a very high energy density. The laser beam is used both to heat and soften the metal in front of the cutter and to perform the cutting process itself when piercing holes, milling and cutting sheet metal, plastics and other materials. The cutting process occurs without the formation of chips, and the metal that evaporates due to high temperature is introduced with compressed air. Nowadays, lasers are used for welding, surfacing, and cutting in cases where increased demands are placed on the quality of this operation. For example, super hard alloys, titanium panels in rocket science, sheet and panel aluminum composite materials, nylon products and wood are cut with a laser beam by burning or evaporation. The high energy density in the heating zone creates an additional effect of cleaning the metal. It should be noted that lasers have a relatively low efficiency due to the conversion of electrical energy into thermal energy and the laser into mechanical energy. Plasma metal processing methods are rightfully considered one of the most progressive. The enormous temperature of the plasma and significant kinetic energy of its jet guarantee high-quality processing of any metals and materials. The power of modern plasma installation reaches 6 megawatt. The use of plasma and laser processing methods is especially effective in the manufacture of parts of complex shapes. When chemically exposed to various reagents, a film of reaction products forms on the surface of the metal, which can isolate it from the reagent and prevent the further courses of the reaction. If this film is periodically removed, the reaction will continue and the metal at the site of its occurrence will be destroyed. In order for such a process to be controllable, it is necessary to ensure a certain composition and properties of the film as well as the rate of its formation. The essence of electrochemical processing is the electrochemical anodic dissolution of metals. Next time, beam and ultrasonic methods of materials processing. Electron beam methods use next item. Electron beam methods use thermal energy released when a stream of fast-moving electrons collides with matter. The high energy of the electron beams is achieved by accelerating electrons in high voltage field, like in figure 14.5 installation diagram for electron beam processing. Precision dimensional processing with an electron beam is carried out in a special installation. All functional systems of the installation are contained in chamber 3, where a vacuum of 0.1333 micropascal is maintained. The source of free electrons is a hot tungsten filament cathode. Under the influence of high voltage electric field created by anode 2, the electron beam acquires high speed and rushes to the workpiece 7, installed on the movable table 5. Focusing the electron beam into a narrow beam and controlling the trajectory, its movements are carried out using electromagnetic lenses 4, 5, 6, which have independent power sources. The cross-section of the focused beam can reach 10 pm square, which ensures a high specific energy density. Using a special generator, energy is supplied in pulses with a frequency of from 50 to 5000 Hz and duration of 100 or 1 microseconds. Electron beam processing has a number of advantages that make its practical use expedient. These are high energy concentration and degree of local cating, allowing the processing of miniature parts, small diameter holes, etc. The ability to widely regulate modes and control the process, the ability to process both metallic and non-metallic materials of almost any hardness, increased cleanliness of the environment during processing and the absence of oxidizing of pollution substance, which allows the processing of highly reactive and refractory metals. The ability of process areas that cannot be processed by other methods. Processing with a light beam is carried out using a beam generated and emitted by an optical quantum generator, a laser. Laser is a physical device that emits coherent monochromatic light in the form of a highly focused beam with a high energy density. The principle of its operation is as follows. If with the help of an external energy source, atoms of a substance are transferred to an excited state, then upon transition to one of the lower energy levels, they will emit light quanta. Such a change in the energy state of atoms under normal conditions, for example, in incandescent lamps, occurs involuntarily. Each atom emits light independently of the others at some random moment, not coherently, resulting in a wide spectrum of non-monochromatic radiation propagating in all directions from the source. The formation of a directed beam from such a source through optical systems is accompanied by the loss of a significant amount of energy. In a laser, atoms of a substance are excited by a powerful light source, pulsed flash lamp, electron impact, and the energy of chemical reactions, forces, for example, electromagnetic waves of the same frequency as frequency of the light released. As a result, atoms emit light quanta synchronously, which makes it possible to obtain intense coherent radiation. Solids, liquids, and gases are used as active substance in lasers. The most common laser design is with a solid active substance, a cylindrical rod of ruby single crystal, or a rod of neodymium glass. which are also resonators. Streams of light quanta propagating along the axis of the rod and experiencing multiple reflections from its end mirror faces are focused in a very narrow beam with a diameter of up to 1 micron, the specific power of which reaches 1 terawatt per square meter or more. The light beam processing process is similar to the electron beam processing process and is used for the same purpose. Lasers operate in pulsed mode, providing a high level of local heating. They are compact and high performance, for example, with a laser power source of several tens of kilowatts, 30-60 holes per minute, with a diameter of 0.03–0.5 millimeters, are 7 at a depth of tens to several millimeters. The process can take place in any atmosphere. Optimal parameters of zero mode for processing specific materials are still selected empirically. Next type, ultrasonic processing of materials. Like in figure 14.6, scheme of ultrasonic processing of materials. The alternating current of ultrasonic frequency produced by the generator 7 enters the excitation coil 2 of the magnetostric rod 3. An alternating magnetic field of the same frequency is created in the coil. Under the influence of this field, the rod vibrates, and its vibration with a frequency of 1530 kHz and an amplitude of 2060 micrometers are transmitted to tool 4, to the processing zone, into the clearance between the end of the tool and the workpiece 5, liquid, water or oil, with abrasive particles suspended in it supplied through a nozzle 6 from a centrifugal pump. Cutting occurred due to a large number of directed micro-impacts of abrasive particles on the surface of the workpiece, causing chipping of small particles of material. The tool installation for ultrasonic processing is made of structural steel 40, 45, and 50. Its shape and cross-section determine the profile of the cavity being processed. Boron carbide or silicon carbide with a grain size of 310 is used as an abrasive. Examples of the use of ultrasonic processing include the following processes: manufacturing of hard alloy matrix, grinding of quartz, agates, jasper ferrites, citals, ceramics, hard alloys, processing of semiconductor materials, cutting narrow grooves and trading in parts made of hard alloys and ceramics. In addition, ultrasonic vibration make it possible to significantly intensify the processes of chemical and electromechanical etching, washing, etc. The accuracy of ultrasonic processing can reach 7-6 grades, surface roughnesses 8-10 grades. And we start item 14.3. Efficiency of new methods of metal processing. New methods of metal processing bring the technology of manufacturing part to a new higher level compared to traditional technology. This is the most effective technology, most often non-waste. General advantages of new processing methods: no need for special tool materials of high hardness, practical independence of productivity from the rigidity and other properties of the material being processed, reduction of the required force impact on the workpiece during processing, with the exception of hydroplastic processing, simplicity of machine design, easy of automation of the processing process, etc. Thus, labor productivity during ultrasonic processing compared to traditional cutting methods increases by 10-20 times when making non-circular holes and 2-3 times when making round ones. At the same time, material savings range from 20 to 50%. Using hydroplastic processing, it is possible to punch any hole in a foil with a thickness of only a few tens of micrometers, produce indentations and hole in the pipe wall from inside, and prepare 3-layer pipes from different materials. The equipment is 10 times cheaper than with mechanical processing methods and ensures complete labor safety. Labor productivity increases and almost 100% metal utilization is achieved, as well as significant energy savings. Program-controlled electric spark machines can be successfully used in the manufacture of parts for televisions, cars, aircraft, and other engines. The processing accuracy on them is ±1 micron. The introduction of equipment for plasma cutting and mechanical processing of parts helped to increase labor productivity by 5-10 times. The laser beam can scan the surface of parts that have extremely complex shapes, gas turbine blades, and other, and perform it processing. This ensures a cutting speed of up to 8 meters per minute. When processing products made of carbon and corrosion-resistant steel, titanium, and special alloys. Similar results are achieved using other new processing methods. And the last item of our lecture, item 14.4, technical and economic characteristics of the use of new methods of processing materials. The main indicators that determine the economic efficiency of using new methods are capital costs and production costs. Determine economic efficiency in the following areas. Comparison of new methods with mechanical ones. When two options are compared and the advantages of one type of processing are easily determined. Assessment of the economic efficiency of such technological processes that cannot be performed in other ways. And here it is necessary to take into account the economic effect of the further use of new methods. Replacement of materials, new design possibilities for using materials, etc. Determination of the economic effects by reducing production costs while reducing tool costs, eliminating or sharply reducing defects. The use of new methods of processing materials allows not only to increase labor productivity, but also to significantly reduce the labor intensity of production of many types of products. So, if the labor intensity of manufacturing a forging die by million on universal and copy milling machines is taken as 100%, then the complexity of manufacturing it on an electric pulse machine will be 20-30%. Application electrophysical chemical processing methods provide accelerated growth in labor productivity, open up new possibilities for manufacturing products while reducing the labor intensity of production and insignificant capital costs. When the beam touches the metal, the energy of the electrons turns into heat and instantly heats the metal to a temperature of 6,000 degrees of Celsius, due to which it evaporates at this point. The pulsed operating mode of the electron gun and the high energy density of the electron beam make it possible to create a high level of local heating. The process is monitored using an optical microscope. So it was the last item of our lecture. If you have the questions, you can tell me, or you can write it to our Telegram group. You can write it to our forum on the course. For now, the time of our lecture is finished.